June 8, 1944, 11:47 p.m. The small French town of Saumur. 19 Lancaster bombers roar overhead at 18,000 feet, each carrying something the Germans have never seen before. A single bomb. Not a payload of dozens, just one. 12,000 pounds of precisely engineered destruction that's about to do something impossible. Deep below the hillside, German panzer tank crews sleep soundly inside a railway tunnel reinforced with 60 feet of solid rock and earth. The Nazis believe this tunnel is invulnerable. They're wrong. Because what drops from those Lancasters isn't just a bomb. It's a weapon that breaks the sound barrier while falling. A projectile so aerodynamically perfect, so ballistically advanced, that it achieves what no bomb has ever done before. It turns physics itself into the weapon. When that first Tallboy punches through the hilltop, it doesn't stop at the surface. It doesn't explode on impact. Instead, it bores through 60 feet of rock like a drill bit through butter, enters the tunnel, and then detonates deep underground. The entire hillside moves. The tunnel collapses completely, and the German panzer reinforcements heading to Normandy, they never arrive. But here's what makes this weapon truly remarkable. The man who designed it calculated everything on paper 3 years earlier, in 1941, without computers, without testing, using nothing but mathematics and revolutionary engineering principles that would change warfare forever. This is the story of how one British engineer solved an impossible problem. How do you destroy targets that conventional bombs cannot touch? How do you penetrate concrete bunkers 20 feet thick? How do you sink a battleship that survived everything thrown at it? The answer wasn't more explosives. It was smarter physics. And the result was the Tallboy, an earthquake bomb so advanced that pieces of its design philosophy are still used in modern bunker busters today. By 1943, the Allies faced a critical engineering challenge that traditional bombing could not solve. Nazi Germany had constructed submarine pens along the French coast with reinforced concrete roofs up to 20 feet thick. V-weapon bunkers featured concrete domes 5 meters thick. Underground factories were buried beneath mountains. The battleship Tirpitz, hiding in Norwegian fjords, threatened every Arctic convoy supplying the Soviet Union. The RAF had thrown everything at these targets, thousands of conventional bombs. The result? Barely a scratch. Standard high-explosive bombs carried thin casings designed to maximize explosive content. When they hit concrete, they shattered on impact, their energy dissipating harmlessly against the surface. Enter Barnes Wallis, a 56-year-old aeronautical engineer at Vickers Armstrong. He'd already gained fame for designing the geodetic construction method used in the Wellington bomber and, more recently, the bouncing bomb that breached German dams in Operation Chastise. But Wallis had been thinking about a different kind of weapon since 1941. In his paper titled A Note on a Method of Attacking the Axis Powers, he proposed something radical. Forget trying to blast through the fortifications, go around them. Or rather, go beneath them. His concept was elegantly simple but engineering challenging. Drop a massive bomb from extreme altitude. Make it so aerodynamically perfect that it achieves unprecedented velocity. Instead of exploding on the surface, design it to penetrate deep underground next to the target, then detonate. The explosion wouldn't need to break through the concrete. The shockwaves traveling through the earth itself would shake the target's foundations to pieces. An earthquake weapon that turned geology into an accomplice. Wallis originally envisioned a 10-ton bomb dropped from 40,000 feet. There was just one small problem. No aircraft in the RAF inventory could carry it. His proposed Victory bomber design was rejected by the Air Ministry as impractical. So Wallis adapted. If he couldn't have his 10-ton bomb, he'd create something smaller that could still work. The Tallboy would weigh 12,000 pounds, half his original design, but still twice the size of any bomb currently in use. But they didn't know was whether this radical theory would actually work in practice. Wallis was betting everything on calculations made with slide rules and mathematical intuition. The challenge now became pure engineering. How do you create a bomb that could survive impact at speeds approaching 750 miles per hour? And how do you make it penetrate solid Earth without breaking apart? And most challenging of all, how do you make it accurate enough that bombers at high altitude could actually hit what they were aiming at? The answers to these questions would require engineering breakthroughs that had never been attempted before. The Tallboy's design was revolutionary in ways that conventional weapons engineers had never attempted. First, the aerodynamics. Wallis made the bomb ridiculously streamlined. 21 feet long with a maximum diameter of just 38 inches. The shape wasn't cylindrical like traditional bombs. It featured a precisely calculated ogive nose that would slip through air with minimal drag. The tail section comprised half the bomb's total length, fitted with angled fins that did something clever. They induced spin. As the Tallboy fell, those angled fins caused it to rotate like a rifle bullet. This gyroscopic stability prevented tumbling and yawing, keeping the bomb pointing nose down throughout its 37-second descent. Early prototypes without spin tumbled unpredictably. The twisted fins solved this completely. But aerodynamics alone weren't enough. The real engineering challenge was the casing. Traditional bombs used thin steel casings to maximize explosive payload. They were designed to fragment on impact, creating shrapnel. The Tallboy needed the opposite, a casing so strong it could punch through concrete and earth without shattering. Wallis specified high tensile steel for the entire bomb body, cast in a single piece at the Vickers River Don Works in Sheffield. The casing had to be over 4 inches thick in critical areas. After casting, the steel took 2 full days to cool before the painstaking machining process could begin. Here's where it gets fascinating. To maximize penetration, Wallis designed a massive hardened steel plug that was precisely machined and fitted into a recess in the bomb's nose. This plug acted like a drill bit, concentrating the impact force into a small area. The entire nose section had to be perfectly symmetrical. Any imbalance would cause the bomb to veer off course during its high-speed descent. The filling was Tirpitz, a more powerful explosive than TNT, comprising 5,200 pounds of the bomb's total weight. The remaining 6,800 pounds was steel casing. Traditional bombs were about 70% explosive, 30% casing. The Tallboy reversed this ratio. 43% explosive, 57% structure. This was necessary to survive the impact forces. Manufacturing each Tallboy was labor-intensive and expensive. After the steel casing was machined, workers poured molten Tirpitz by hand into the base of the upturned bomb. Once the Tirpitz set, they sealed it with a layer of pure TNT, then a 4-inch composite layer with recesses for 3 chemical time delay fuses. 3 fuses, not 1. Redundancy was critical. Even if 2 fuses failed, the third would trigger detonation. The delay could be set from 30 seconds to 30 minutes after impact, giving the bomb time to penetrate before exploding deep underground. Now came the velocity problem. For the Tallboy to function as designed, it needed to achieve something unprecedented: supersonic velocity in freefall. The speed of sound at sea level is approximately 767 miles per hour.
Wallis calculated that his bomb, dropped from 18,000 feet, would reach 750 miles per hour at impact. That's roughly 3,700 feet per second. Some estimates suggest it actually exceeded the sound barrier during descent. Think about what this means. The bomb was breaking the sound barrier before anyone had built an aircraft that could do so. The first supersonic aircraft flight wouldn't occur until 1947 with Chuck Yeager in the Bell X-1. But the Tallboy was already going supersonic in 1944, creating its own sonic boom as it plummeted toward the target. This supersonic speed was critical for penetration. At impact, the bomb's kinetic energy was enormous. Physics tells us that kinetic energy equals 1/2 mass times velocity squared. Double the speed, and you quadruple the energy. The Tallboy's combination of mass and velocity gave it penetration capabilities far beyond anything previously attempted. When it hit concrete, tests showed it could penetrate 16 feet before detonating. When it struck Earth, it could bury itself 80 feet deep, creating a crater 100 feet across and 80 feet deep. The earthquake effect Wallis had calculated in 1941 actually worked. But there was another consequence of this speed that nobody had fully anticipated. Like the German V-2 rocket, the Tallboy traveled faster than its own sound. People on the ground heard the explosion before they heard the bomb falling. The psychological effect was terrifying, a massive detonation with no warning whatsoever.
This precision weapon required precision delivery. The Avro Lancaster was Britain's premier heavy bomber, but carrying a Tallboy required radical modifications. First problem, weight. At 12,000 pounds, the Tallboy weighed twice as much as a typical full bomb load. Something had to go. Engineers stripped out the Lancaster's armor plating. Then they removed defensive armament, including the mid-upper gun turret and sometimes even the nose turret. These Lancasters became known as Lancaster BI Special. They sacrificed protection for payload capacity. The crews flying these missions were essentially undefended, relying entirely on altitude and fighter escort for survival. Second problem, the bomb bay. The Tallboy was 38 inches in diameter. Standard bomb bay doors couldn't accommodate it. Engineers had to modify the doors so they could bulge around the bomb's girth and still close. In some cases, they removed the doors entirely and cut away part of the rear bomb bay to clear the bomb's tail. The bomb hung so low that ground clearance became an issue. Lancasters carrying Tallboys had to be extremely careful during takeoff, making sure not to strike the runway with the protruding weapon. Third problem, accuracy. The standard Mark 14 bomb sight wasn't precise enough for the Tallboy's mission requirements. The RAF introduced the Stabilizing Automatic Bomb Sight, or SABS. This was an analog computer that continuously calculated the bomb's trajectory based on altitude, airspeed, wind direction, temperature, and the bomb's ballistic characteristics. The SABS was sophisticated but temperamental. It required crystal-clear visibility of the target. Bombardiers had to account for numerous variables and make corrections during the bombing run. But when used correctly, it was devastatingly accurate. Number 617 Squadron, the famous Dam Busters, achieved an average accuracy of 170 yards from 18,000 feet. For comparison, standard area bombing was considered successful if bombs landed within 1,000 yards of the target. Training crews to use the SABs took weeks. Bombardiers practiced constantly, calculating corrections for different conditions. The entire mission depended on that moment when the bomb released. Too early, too late, wrong altitude, wrong speed, any of these meant failure. And because Tallboys were expensive and difficult to produce, crews were ordered to bring unused bombs back to base rather than jettison them. Landing with a 12,000-pound bomb still aboard added significant risk, but the weapons were too valuable to waste. Each Tallboy represented hundreds of man-hours of skilled labor and expensive materials. They weren't expendable. The Lancaster had to be at exactly 18,000 feet, traveling at precisely 170 miles per hour forward speed. The bombardier would begin his calculations minutes before the drop, feeding data into the SABs.
The autopilot connected to the bomb site would make final adjustments. Then, at the precise calculated moment, the Tallboy would release. 37 seconds of freefall. The crew would watch it disappear, a dark shape accelerating toward the Earth. Then they'd wait. Sometimes, the earthquake effect was visible from the air, the ground literally rippling from the underground detonation. Other times, thick clouds of debris would erupt from impact craters 80 feet deep. But would it work on the first combat mission? Nobody knew for certain until that night in June 1944, over a French railway tunnel near Saumur.
June 8, 1944. 2 days after D-Day. The first Tallboy mission targeted the Saumur railway tunnel in France. German panzer divisions were attempting to reach Normandy to counterattack the Allied beachhead. The fastest route ran through a railway tunnel near Saumur. If the Allies could collapse that tunnel, they could delay German reinforcements by days, maybe weeks. 19 Lancasters from 617 Squadron, led by Wing Commander Leonard Cheshire, loaded Tallboys and took off in darkness. 6 additional Lancasters carried conventional bombs. The target? A hillside with 60 feet of rock covering a railway tunnel. Pathfinder aircraft from 83 Squadron marked the target with flares. At precisely 11:47 p.m., 617 Squadron began their bombing run from 18,000 feet. The bombardiers tracked their targets through the SABs, making minute corrections as the Lancasters steadied on their approach. The first Tallboy dropped. 37 seconds of freefall. It struck the hilltop and disappeared. Then came the earthquake. The massive bomb punched completely through the hill, entered the tunnel nearly 60 feet below the surface, and detonated inside. The explosion was catastrophic. The tunnel roof collapsed. Debris filled the passage. The railway was completely blocked. Several other Tallboys struck nearby, creating enormous craters and further destabilizing the area. When German engineers arrived to assess the damage, they found destruction that was unprecedented. One bomb had created a crater so deep they could see the tunnel interior exposed. The mission was a complete success. Not a single Lancaster was lost. The tunnel remained blocked for months. Panzer reinforcements heading to Normandy had to find alternate routes, delaying their arrival during the critical first weeks after D-Day. The Tallboy had proven itself. But this was just the beginning. Over the following months, Tallboys devastated targets across occupied Europe. June 19, 1944, Wartime bunker, a massive V-2 rocket facility with reinforced concrete walls and roof. A Tallboy landed 50 yards away and exploded underground. The shockwaves undermined the bunker's foundations. The structure shifted, became unusable. The Nazis abandoned it. June 24, 1944, Wisernus, also known as La Capole, another V-2 site featuring a concrete dome 5 meters thick. Multiple Tallboys hammered the area. None penetrated the dome directly, but several exploded beneath it. The seismic shocks destabilized the foundations. The dome shifted out of alignment with the support structure. Once again, the Germans abandoned the facility. This became the pattern. The Tallboy rarely needed a direct hit. Exploding near the target was often sufficient. The earthquake effect did the work, transmitting shockwaves through rock and soil into the structure's foundations. Buildings could be hardened against surface explosions, but foundations couldn't be hardened against seismic shocks traveling through the Earth itself. August 5, 1944, Brest submarine pens. 15 Lancasters attacked with Tallboys. 6 direct hits penetrated the reinforced concrete roofs. U-boats inside were destroyed. The pens were rendered unusable. The Germans began reinforcing other submarine facilities with even thicker concrete, diverting resources and manpower from other projects. Every successful Tallboy mission validated Wallis's theories. The earthquake bomb concept worked exactly as he had predicted on paper. 3 years earlier. But the weapon's most famous target was still waiting. The Tirpitz was Nazi Germany's last operational battleship, sister ship to the Bismarck. Hidden in Norwegian fjords, protected by anti-aircraft batteries, smokescreens, and torpedo nets, she posed a constant threat to Allied Arctic convoys. Previous attacks with conventional weapons had failed. The Tirpitz seemed unsinkable. But the RAF had a new weapon specifically designed to crack impossible targets. September 15, 1944, Operation Paravane. Lancaster bombers flew from bases in Scotland, pushing their range to the absolute limit. They found the Tirpitz in Kofjord, Norway. 27 Lancasters attacked with Tallboys. One bomb struck near the bow. The Tallboy penetrated the foredeck, passed through the hull, and exploded in the water beside the ship. The blast was devastating. Hull plates buckled, forward compartments flooded with 2,000 tons of water. The bow was wrecked. The Tirpitz was rendered unseaworthy. She required 9 months of repairs that the Germans couldn't afford. Instead, they moved her to Tromsø to act as a floating artillery battery. The RAF wasn't finished. If the Tirpitz couldn't be repaired, she would be destroyed. November 12, 1944, Operation Catechism. The final mission. 32 Lancasters from numbers 9 and 617 squadrons attacked the Tirpitz in Tromsø harbor. The smokescreen failed to fully deploy. Visibility was perfect. The bombardiers had clear sight of the massive battleship. The Tallboys fell. This time, the bombing was devastatingly accurate. 3 direct hits. The first bomb penetrated between turrets Anton and Bruno, but failed to explode, a rare malfunction. But the other bombs more than compensated. The second Tallboy struck amidships, between the aircraft catapult and the funnel. The explosion was catastrophic. It completely destroyed the entire section of belt armor and blew a massive hole in both the ship's side and bottom. Water poured in. The ship began listing to port. The third bomb struck turret Caesar on the port side. The explosion penetrated deep into the ship's interior. Moments later, the magazine detonated. The secondary explosion was enormous, visible from miles away. The Tirpitz's back broke. Within minutes, the 42,000-ton battleship capsized. She rolled to port, her hull breaking the surface like a breaching whale, then settled upside down in the shallow harbor. Of her 1,900 crew, nearly 1,000 died, many trapped inside the capsized hull. The last major surface threat to Allied shipping was eliminated, not by naval warfare, not by torpedoes, but by earthquake bombs dropped from the sky. The Tirpitz, which had survived countless attacks with conventional weapons, was destroyed by 3 Tallboy hits. This success demonstrated the Tallboy's ultimate capability. It could destroy targets that were previously considered invulnerable. Battleships with 16-inch armor plate, submarine pens with 20-foot concrete roofs, underground bunkers carved into solid rock. The Tallboy made them all vulnerable. And Wallis was already thinking bigger.
The success of the Tallboy proved Barnes Wallis's theories correct. But Wallis wasn't satisfied. If a 12,000-pound bomb could do this much damage, what about something bigger? By late 1944, the Lancaster had been modified extensively enough that it could potentially carry something heavier. Wallis went back to his original 1941 concept, the 10-ton earthquake bomb. The result was the Grand Slam, 22,000 pounds, at the time the heaviest conventional bomb ever created. It used the same principles as the Tallboy, but scaled up, longer, heavier, even more aerodynamically refined. The penetration capabilities were extraordinary. The first Grand Slam was dropped on March 14, 1945, against the Bielefeld Viaduct in Germany. The massive bomb created an earthquake effect so powerful that 100 meters of viaduct collapsed not from direct hits, but from the foundations being liquefied by seismic shock. The Grand Slam could penetrate over 100 feet into soil before detonating.
But the Tallboy continued its operational career right up to the war's end. The missions kept coming. On April 9, 1945, Tallboy sank the German pocket battleship Admiral Scheer in Kiel Harbor. 5 direct hits caused the ship to capsize. On April 16, 1945, they attacked the heavy cruiser Lutzow in Schweinemunch, Poland. Despite intense anti-aircraft fire, 15 Lancasters managed to bomb the target. One near miss with a Tallboy tore a massive hole in the bottom of the ship. The Lutzow settled to the bottom in shallow water. 1 Lancaster was lost, 617 Squadron's last loss of the war. Remarkably, one of those Tallboys remained buried in the mud for 74 years until it was discovered during dredging operations in September 2019. In October 2020, while attempting to defuse it, the bomb detonated underwater. Fortunately, no injuries occurred. The final Tallboy mission occurred on April 25, 1945, just days before Germany's surrender. The target? Adolf Hitler's Berghof residence near Berchtesgaden. 6 Lancasters from 617 Squadron dropped their last Tallboys on the mountainside retreat. The bombing was accurate and effective, symbolically destroying Hitler's vacation home as the Third Reich collapsed around him. Between June 1944 and May 1945, the RAF dropped 854 Tallboys and 41 Grand Slams. The success rate was remarkable. These weapons destroyed U-boat pens, V-weapon sites, railway viaducts, bridges, battleships, and heavy fortifications that conventional bombing could not touch. The engineering principles Wallis pioneered lived on long after World War II ended. Modern bunker buster weapons like the American WW2 used the same fundamental concept: a hardened penetrator casing, precision aerodynamics, delayed detonation, and the earthquake effect. The WW2 is even nicknamed Deep Throat for its ability to penetrate underground bunkers in a way that echoes the Tallboy's capabilities 80 years earlier. The United States developed their own version called the T-10, later redesignated the M121. During the Korean War, some of these were converted into radio-guided Tarzan bombs and used to destroy bridges and dams. During Vietnam, M121 warheads were incorporated into the massive BLU-82 weapons dropped by C-130s, including one used during the Battle of Hamburger Hill in 1969. But what makes the Tallboy truly remarkable isn't just what it accomplished, it's how it was designed.
Barnes Wallis calculated everything in 1941, using nothing but slide rules, mathematics, and engineering intuition. He predicted exactly how the bomb would behave, how fast it needed to fall, how deep it would penetrate, how the shockwaves would propagate through rock and soil. And when the Tallboy was finally built and tested 3 years later, it performed almost exactly as he had predicted. The first combat mission at Samur worked perfectly on the first attempt. No prototypes had been combat tested. The math was right, the engineering was right, the physics worked. This wasn't trial and error. This was pure engineering brilliance. Wallis understood something profound that other weapons designers had missed. The problem wasn't that conventional bombs weren't powerful enough. The problem was that they released their energy in the wrong place, at the wrong time, in the wrong way. The Tallboy solved all 3 issues simultaneously through intelligent design. Today, when you hear about bunker buster weapons penetrating underground facilities, understand that the Tallboy pioneered that concept 80 years ago. The principles Barnes Wallis established remain valid. Deep penetration requires aerodynamic perfection. Delayed detonation underground creates more damage than surface explosions. Seismic shockwaves can destroy foundations that surface bombardment cannot touch. Precision matters more than payload size. Modern weapons have guidance systems, laser designation, GPS targeting, but the fundamental engineering that makes them work, that comes directly from Barnes Wallis and his Tallboy bomb. His calculations were so accurate that contemporary weapons still follow his design philosophy. The Tallboy represents something remarkable in engineering history, a weapon designed on paper that worked exactly as calculated on its first combat use. No computer modeling, no iterative testing, just mathematics, physics, and extraordinary engineering insight. It's a reminder that engineering isn't about brute force. It's about understanding the problem deeply and applying scientific principles creatively. Wallis didn't have more resources than other engineers. He had better insight into how to use the resources available. The crews who delivered these weapons faced extraordinary challenges. Flying modified Lancasters with reduced defensive armament, they were vulnerable to German fighters. The missions required flying in daylight for visibility, often at extreme range. During the Bergen submarine pen raid, 4 Lancasters were shot down. During attacks on the Tirpitz, crews flew sorties that pushed fuel limits to the maximum. The accuracy required meant stable, straight bombing runs that made them easy targets for anti-aircraft fire. But they persisted, mission after mission, delivering the earthquake bombs that changed the war. The Tallboy's secret wasn't that it was bigger or more explosive than other bombs. The secret was that it was smarter. Wallis turned physics into a weapon. He made gravity an ally. He used the Earth itself as a transmission medium for destructive force. And in doing so, he created something that remained effective for decades after the war ended. If you found this deep dive into World War II engineering fascinating, make sure to subscribe. We explore the technical problem-solving stories that changed history, the engineering challenges that seemed impossible until someone figured out the solution. Next time, we'll examine how Allied code breakers cracked German encryption systems through mechanical engineering and mathematical innovation, creating machines that laid the groundwork for modern computing. The Tallboy proved that in warfare, as in engineering, the smartest solution isn't always the biggest hammer. Sometimes it's the precisely calculated strike that uses physics, mathematics, and brilliant design to achieve what brute force cannot. And sometimes being smarter beats being bigger every single time.